Welcome to today's Military and Aerospace Electronics webinar. SOSA is here. What's coming next in 100 gigabit high-speed Ethernet connectivity, sponsored by Concurrent Technologies, ISO Rugged Solutions, and Elma Electronic. I'm John Keller, Chief Editor of Military and Aerospace Electronics. The Sensor Open Systems Architecture, or SOSA, technical standard is receiving accelerated adoption and early deployments in the US and worldwide. More than 160 companies now are designing and delivering SOSA solutions with a growing number of multi-vendor interoperability demonstrations. SOSA is being called on for more and more in programs of record. Having demonstrated interoperability between plug-in cards from SOSA ecosystems partners, this webinar will show how to use these newly unlocked 100 gigabit high-speed bandwidth Ethernet connections to provide resilient systems through innovative backplane connectivity, easily reconfigurable heterogeneous compute solutions by mixing CPU and GPGPU resources, and real-time capability to meet the needs of workload consolidation. The webinar will outline what's on the horizon and what can push systems design to the next level of performance. Our speakers today are Ken Grobe, Director of Embedded Computing Architectures at Elma Electronic, Nigel Forrester, Director of Strategy for Concurrent Technologies, and Chris Fadley, Chief Technology Officer at ISO Rugged Solutions. If you have any technical difficulties during today's session, type your question into the Ask a Question box, and a member of our team will assist you. You also can click on the question mark help button in the upper right corner of the screen. We welcome your questions during today's event and will answer as many as possible. And please feel free to send in your questions at any time by typing your questions into the Ask a Question box and clicking on the send button. Today's session is being recorded and will be available on the Military and Aerospace Electronics website within the next week. You'll be notified by email when the archive is available. So let's get started with Ken Grobe, Director of Embedded Technologies at Elma Electronic. Ken?
Thanks, John. So, good day, everybody. I'm pleased to be here with our partners to talk to you about how high-speed Ethernet can be applied to GPGPUs and sensor applications. I'd like to give you a little bit of background first about how, I think I skipped a slide here. Let me go back. By way of introduction, some of the topics we'll discuss today are design considerations for sensor systems that use GPGPUs and SBCs, profiles that are associated with those, effects of how performance is increasing and what that available performance in these devices may do for you, and then a new topic about how we're adding Ethernet, or how it's possible to add Ethernet directly to GPGPU PICs. And we'll take a little bit of a time to look at topologies that are available to support development. So when you look at an AI application or a GPGPU accelerated application, it makes use of SBCs, GPGPUs, or FPGA-based accelerators. And in SOSA, the entities or hardware elements that implement these technologies are called plug-in cards, or PICs. And if we look at typical application types, we see things like ISR, EW, and these applications drive the data sets that are specific to these use cases and affect what topologies that we would put together or the system architect would put together to implement them. So typically, GPGPUs use local connections to transfer the data between the SBC resource and the GPGPU itself. And in the case of SOSA, this is done, or OpenVPX, it's done in something called the expansion plane. And then another thing that we can look at is that how GPGPUs are used. Do we just use one or two? And it turns out that as systems are implemented, you may scale the number of GPGPUs and there may be more than one, and you may need to connect them in different ways. So by way of background, what are some of the applications that people can stand up or organizations can stand up today using SOSA-aligned hardware? And here's three of them. These are actual applications that are being implemented, and then they can be stood up on the OpenVPX hardware that we'll be discussing. So one of them is synthetic aperture radar. Another one is general purpose SDR. So software-defined radio and the processing requirements for that within a GPGPU-based environment. And then the third one's a geospatial application. And all these are brought to us by NVIDIA as applications that have been implemented that allow one to process images. In this case, we're looking for fires. Another real-world application that we've done and worked in the team that's here today is an inference model that does several different forms of object detection. And what's showing on the left is that application running, but you can see it running in a small compact frame that's being implemented with just two boards, a single board computer and a GPGPU. So these are real world applications that we've stood up on SOSA-aligned hardware that exists today. So what are some of the technologies that one would use from a software standpoint to implement GPGPU-based applications? And this diagram here and provided by NVIDIA shows what some of those tool chains are that exist that are being leveraged to implement applications. On the top, what we see is the application modality. So geospatial, SAR, radar, SDR, comms, LiDAR, et cetera. Underneath that, we see what libraries and tools are available to actually sit on top of that hardware to implement it. Things like CUDA and TensorRT and DACA and streaming pipeline APIs. These things abstract the application implementation away from the hardware and make it modular, and they're actually quite rich and help one develop an AI application quite quickly. So if we look at the building blocks that are in the system, so on the left, what we have is development chassis, not necessarily deployment, but development that can allow one to interconnect the cards quickly and mix and match what you need in certain topologies that would allow the connectivity necessary to implement a specific application. In the middle, we have an example of a GPGPU, and to the right, we've got examples of a couple of types of processors from concurrent, compute intensive, and IO intensive. So what are some of the design considerations that the system designer has when applying GPGPUs? First off, if we're in the SOSA-aligned environment, we have a constrained set of profiles that we have to take a look at to see how we're going to map IO and then how we're going to interconnect it. Then there's a question of the data paths that are available to interconnect from the devices. And those break into things like control plane and data plane. And then we have speeds that they operate at that are enabled by the hardware itself, but also by the interconnect media, which is the backplane. And that can run from anywhere from 10 gigabits per lane to 25 gigabits per lane. And those lanes support different protocols like Ethernet or PCIe. And ultimately, we need to cast that into some development environment or a, let's say, deployment chassis to be able to affect the system design. So to look at those things in context around the profiles, these are pictures of the actual PICs. We'd have things like compute-intensive SBC payloads, Ethernet networking switch, which is key to the whole infrastructure because this is how the data is moved around relative to the Ethernet protocol. And then we have actually two classes of intensive and one that's IO intensive. And the IO one is self-explaining in the sense that what we're concentrating on that CPU is to bring out various types of IO associated with the single board computer. And then lastly, the accelerator, the GPGPU. and we've got the payloads or the profiles that are appropriate standing next to them. So let me get into that in a little bit more detail. So fortunately, because of the way SOSA has construed what profiles are available, they are constrained. Constrained's kind of a good thing from interoperability, in that the ecosystem builds to these profiles, and then because they're all mapped out the same way around a specific profile type, this affords interoperability in that one will be able to interface and plug into a known slot, if you will, and then things are in a predefined place. So anyway, we have two main profiles that are of interest here for compute-intensive SBCs and FPGA accelerators and GPGPUs as we go down through. And one of them is called the primary profile. It's 14.6.11. That applies to the compute-intensive SBC, but it also applies to the GPGPU. So we're pinning them out in the same fashion. And then what we need to do is interconnect between them. And lastly, we have a wider one that's available for high speed or higher, let's say a wider interface, high bandwidth, I guess is a better word to say, where we have more local connections in the PCIe expansion plane, and that's in this blue color here. So moving on, taking a look at how these things are laid out. If we had a single board computer in the blue block on the right and a GPGPU on the left, if we look at the two profiles, what we need to do is interconnect between them, and the primary data between the GPGPU and the SBC is going across the expansion plane, and in this case, the profile affords a by 8 connection between the two. That gives us on the order with PCIe Gen 3 or Gen 4, somewhere between 8 to 16 gigatransfers per second of data transfer between the devices on this local link. So taking a look at where these things are in a backplane topology, the gold bubble points to where the data plane connections are. And above that, we have the local connections or the expansion plane connections. So let me illustrate that a little bit better. Here we've got a backplane topology diagram where green is control, gold is data, and blue is expansion. And when we look at where the modules plug in these two slots, we're seeing primary payload slots adjacent to each other with a single board computer located in one and a GPGPU located in the other. So PPCIe, the PCIe protocol, is connecting the two slots together across the expansion plane. And then there's how the data plane is being used. So in this case, specifically, Ethernet's not being used on the GPGPU directly. So we can take a look at that a little bit more. In this example, we're showing GPGPU being applied adjacent to a single board computer on either side, where you may have two accelerators driven by one host. And here we have the Ethernet connection being made to this SBC and the control plane connection being made to the SBC. And then local instance or local communication taking place across PCIe. So if we look at what's new and what's coming, the ability to transfer data, which would typically be done in the system now over the data plane that's connected to the processor on the right-hand diagram, we can add a connection, which is a data plane connection directly to the GPGPU. The topology has allowed this, and the mapping for that, let's say that wiring in the backplane is there. However, it's not been architecturally possible to do this until just recently, and more practically able to do it with a higher transfer rate that's afforded by gigabit Ethernet. So one other point would be, what do you do when you need to expand the pipes between the two SBCs and GPGPUs? This can be accomplished with a secondary slot profile that's shown here that gives you a wider up to by 16 capability between the two cards. So what are the rates that we're talking about? So for the last, say, 3 to 4 years, we've been looking at Ethernet communications at 110 and 40 gig, or say 40 gig at the high end on the data plane. And where we're going now is with switch matrices that support 100 gigabits and endpoint devices that support 100 gigabit capability. We now can see performance increase from 40 gig, would give you about 2.8 gigabytes per second transfer between 2 points, moving up to 100 gigabit, which gives you around 5 to 9, depending on whether you're using RDMA or other DMA methods. So you're looking at somewhere between a 2 to 3x increase in transfer rate between devices across the network. So what does that look like physically? Physically, as far as interconnect, this is an example of a backplane that implements the logical profiles that are shown below in each place. And this gives us a set of working profiles where you have enough payload connections or let's say payload profiles, a central switch and an IO SBC profile to have sort of a rich set of slots available to stand up a system architecture. And this would be what that looks like when it's mounted in a chassis and something you could use that sits on your desktop. Then this would take between 6 and 8 slot cards. And you'll notice slots that are conduction cooled, so the cards can actually be conduction cooled and run on the desktop in a development environment. So enabling GPGPUs with high-speed Ethernet, why do we want to do that? Or what's the advantage? One of the things it does is it allows direct transfer of the data to the GPGPU for processing through Ethernet in a different pathway across the network. So data could be routed to multiple GPGPUs in this example, and it would also support DSP processing via the GPGPU, or let's say in an RF application where we have I and Q data to move, we can move that data directly from a receiver that may do something like down convert it and then transfer it over to a DSP. To give you an idea of how much bandwidth you could potentially transfer over gigabit Ethernet to 100 gigabit Ethernet, that would be on the order of, let's say, 3 gigahertz worth of spectrum digitized could be moved across that pipe. So this leads to some questions. How does the architecture change? What's different in the software? Because typically what we see is the PCIe-centric connectivity between the GPGPU and the host SBC. Then what are the benefits and where are we with the hardware? Is it existing yet? And for that, I'll segue over to my partners, specifically Nigel, to pick up and take us into the next level. So back to you, John.
Okay, well, thank you, Ken. And now let's turn it over to Nigel Forrester, Director of Strategy for Concurrent Technologies. Nigel?
Thank you very much, John and Ken, for that brilliant sort of segue. So, yeah, good afternoon, good morning. Thank you for joining. So I'm going to sort of slightly sort of build on all of the good stuff that Ken's sort of talked about here. And I'm going to give you a little bit of insight into what we've actually achieved from an Ethernet perspective, and also some of the other use cases for Ethernet that we are bringing to the play here. And I'm predominantly going to talk from an SBC point of view because concurrent technologies, that's predominantly our forte. So, importance of Ethernet. I think Ken's talked quite a lot about, the background as to what SOSA has brought to the play here, where we've effectively promoted a robust ecosystem of providers. The really key part here is that we've removed a lot of the fragmentation. So traditionally, if you roll the VPX clock back 10, 15 years, there were a number of different fabrics that were used to transfer the high bandwidth data, Zero Rapid IO, PCI Express, InfiniBand, and Ethernet. By transitioning to an Ethernet-based data plane fabric, and also some of the other ways of removing the user I/O, it's brought a different class of, it's brought the sort of products that we're making to be much more future-proof and much less vendor-specific. So from a user perspective, there's lots and lots of advantages there. And as part of that, this transition to 100 gig, I've had quite a few people say to me, well, we don't need 100 gig. Probably our application's fine with 10 gig today. But the reality is that by giving you the ecosystem and the building blocks that are 100 gig capable, especially at the platform level, as Ken was talking about, what that really means is we're building future-proof capability into your products. So you can actually update those as you need or transition to new payloads exactly as you need. So I'm definitely going to give you some insight into what we've done there and how that's performing. But I'm also going to talk a little bit about time-sensitive networking for real-time connections, because that whilst it is at the other end of the scale, is also critical to some of the applications that are looking to deploy these social aligned platforms in. So let's start at the high end and give you some sort of benchmark capabilities, because many people have said to me, well, 100 gigs sounds good. Does it actually work in practice? And Ken was talking about some of the interop stuff that we've done together as a group. And I'll give you one primary example that we've done here. So this is using two of our SPCs with 100 gig capable data plane connections linked via a 100 gig switch. They happen to be running Ubuntu. You can see the version on the screen. If you want more information, you can come and ask us. We used a standard IPEV3 bandwidth measuring application so that we made sure we were doing the right thing. And using that with 7 instances of IPEV, we were able to achieve a bandwidth between those two boards of 94.3 gigabits per second. That's pretty much what you'd expect. We've got a 100 gigabit pipe. You should be able to achieve 100 gigabits, except there's a bit of overhead in Ethernet. So no great surprises here, but it proves that you can do that. And if we try that with the real-time extensions enabled, or the real-time kernel, the Linux preempt real-time kernel, we get a very slight reduction in bandwidth because there's a slight overhead that's around the real-time extensions. But again, we achieved 92.6 gigabits. Now, what you probably say is, well, that's totally theoretical. Some of the things that both Ken was talking about, transferring high bandwidth data between CPUs and FPGAs and other bits in the system, and some of the information that Chris is going to talk about in his presentation, let's be a bit more realistic. Is there a way that we could actually provide you a realistic benchmark? And so what we did was we also did exactly the same test, but used an RDMA test suite, I suppose you'd call it. And there we also managed to achieve with exactly the same cards, exactly the same Linux. We got 88.2 gigabits per second. So great, we proved that we can transfer large amounts of data across these pipes should you need or when you need it for your application. What else are we going to do moving forward? So I want to spend a little bit of time talking about what else we can do with those Ethernet pipes. So by having SOSA aligned processors, GPUs, FPGAs, that's really good, but they actually have no user I/O, so that there is one of the two processor devices that Ken showed is the I/O intensive processor, and there you can fit an XMC to provide some I/O. That is defined within the profile. But in a lot of these traditional systems, they've had legacy real-time protocols. I've got some good examples on the screen here. And they basically, send small amounts of data, but in a very deterministic fashion, which is exactly where there is a gap in traditional Ethernet. Fundamentally, it's based around sort of best case, and it retries if it gets a conflict, and so there's some potential issues there. The solution is this thing called time-sensitive networking, because what that does is separates out the real-time traffic from the less critical traffic to provide a viable pipe for by using Ethernet for both your real-time and your non-real-time traffic. So what is time-sensitive networking? It's basically a collection of standards, IEEE standards, which do things like synchronization, shaping, scheduling, and configuration resource management. It grew out of a working group that was around audio-visual bridging. So a very good example, really, in that we're on a video bridge today. Hopefully, the audio is working really well, and you can see that synchronized with the video, so that it gives you a convincing result. It's a very workable example of why you need, in some cases, time-sensitive networking. So how does it work? It uses the idea of profiles. So effectively, it's a collection of things that enable you to select the features and configurations that you want for the type of application that you're doing. That's probably best explained or shown on the next slide. So along the top, you can see there are different profiles. Some of these are further developed than others, and this slide is probably a bit out of date. I think some of the standards work has actually moved forward. So the things in purple at the time that I grabbed this slide, which was about 6 months ago, are still work in progress. Some of those will have actually moved on. And you can see on the right there is an aerospace profile specifically for aerospace applications. And what you need to think about from a time-sensitive networking perspective is the things in the middle here, the components, are that there are lots of things that can help you with synchronization, reliability, latency, and resource management. And it's almost like a pick and choose type scenario where there are specific protocols for specific types of profiles. So it's quite flexible and very comprehensive. And what that does in reality, I mean, I've picked some of the common protocols. So in a particular application, you might need some time synchronization. You might need some traffic shaping. So you can see I've listed the specific IEEE profiles, and the sort of products that we can provide today actually have these protocols enabled, or some of them do. And all of those need to be configured. So the real key to getting a time-sensitive network working is that everything that you want to be time-sensitive within that network has to be configured. It's not a simple task to do that, and so the configurator is really the real key, because you have to determine and tell the elements within that network, or what is hard real-time, soft real-time, or best effort traffic. I've got 4 very simple slides to sort of explain that. So in the first slide, I've got a typical non-time sensitive networking capable VPX system, where it has a switch and that links some CPUs, and there's a GPU, and there's an FPGA, and there's a couple of storage devices. And all of those are served using standard Ethernet best effort traffic. So the little green boxes are simulating the traffic, basically. Now, if you turn that into, or configure that for to be time sensitive, then you can see now I've got red and green little boxes on each of the payloads there, except this one of the storage boxes. So it's perfectly possible to use non-time sensitive and time sensitive elements within the same system. Obviously, if you have something that's not time sensitive capable, it cannot operate in real time. So it will just operate in on a best effort type basis again. But the other elements in this system, this theoretical system I've shown here, are time sensitive capable, and so you can use those accordingly. Now, I talked at the start about what you need to do from a point of view of moving towards time-sensitive networking. So at the moment, a lot of the legacy interfaces still exist on the platforms that we're putting these products into. So those might be things like I've got on the follow-on slide here, where we've got some 429 or 1553 or CAN bus traffic. And there's a way that you can do that and still remain social aligned by fitting an XMC module onto one of those IO intensive processor boards and actually do that. And there's also another way that you can do that by using an external gateway. So you could have your whole system time sensitive capable and actually then link out to a gateway that is non-time sensitive. A gateway that would then bridge your time-sensitive networking with your legacy real-time interfaces. So that's a bit of a lightning tour of time-sensitive networking. As I said, it's completely the opposite extreme to the high bandwidth type of networking capability that I talked about at the first end, because many of these types of systems will be very small packet sizes, but with very critical
I'm on a webinar I'm about to do. I can't talk.
And so with that, I'm going to turn back over to
30
John
minutes.
and hear a bit about Chris's GPUs.
Okay. Well, thank you, Nigel. Our next speaker is Chris Fadley, Chief Technology Officer at ISO Rugged Solutions. Chris?
Thanks, I appreciate it. And I appreciate everyone attending here. So we obviously focus a lot on the GPU sector. That's a lot of where our products are. So when we talk about, GPUs and where things are going with high performance processing, especially in the embedded space, we got to look at the value add of GPUs and why they should be considered now, even if we're in the process of, pulling a lot of historically legacy items forward. So playing off a slide that kind of Ken had when we're looking at, SDRs and geospatial and different radar applications, the value out of a GPU really is it's truly a software-defined engine that can mate with your CPU and then be very quickly repartitioned and edited at a software layer for different modalities. So to give a prime example of this, I'll kind of pull demonstrations that we've done at trade shows over time. So this was a platform that Ken had showed off with the SBC and the GPU next to each other, taking in video into the CPU complexing, RDMAing it into the GPU engine. And again, with the flexibility of this coprocessor, you can perform AI/ML, traditional GPU operations, render it, encode it, it has a built-in encoding engine, and then send that out over Ethernet or optionally upwards to a display. And with that exact same hardware, right, we don't have to change the engine, we change the IO interfaces and add in an SDR complex. So throwing an FPGA and an additional payload slot, and side by side using the same hardware can do the same processing. So this is something we demonstrated recently at AUSA and other trade shows recently, where we have the video complex running side by side with actually SDR, same hardware doing the actual processing, doing typical SDR operations once it's available, the IQ payloads, as you can see here. And one of the important things to consider about GPUs, right, are scale and size and power, and really focusing on the outset of, okay, if I'm going to be adding a GPU platform to my architecture, I need to consider both the future as well as the higher level constructs of thermals, performance, and so on. So common topologies before going into Ethernet today, everything is going to be PCIe bound, and whether that be an XMC, a VPX, or VPX with additional ICs like switches available on there. And with that, there's also classes of GPUs. So there is a GPU series right now, Ampere, which is the one that is readily deployed into production spaces today that are serviced. They can scale all the way down to the smallest grade of an A500 GPU, which can run at 10 to 15 watts, and all the way upwards to an A4500, which can hit 115 watts. And to demonstrate kind of the topology, so to see the different options in the space of how do I add a GPU to my existing architecture. Maybe I have a SOSA-defined backplane and interconnect. How can I add a GPU complex into that? Kind of go over all the different options here. So XMC is still a very viable option, especially for environments that are slot and power constrained. And the IO intensive SBCs out there, or the 14216, are going to be the most readily available XMC enabling devices. So an A500 or an A2000 based XMC product can mate with an IO intensive right out of the box, no edits to the backplane, and act as a local coprocessor to that environment. Again, X4 or X8, depending on the mating XMC card. And there are also options, though rarer, in the compute intensive payload profile, which can be found more prevalently within backplanes where there are XMC sites. So that is also something to consider, is it may not be limited necessarily just by the IO-intensive slot profiles. Once you get into the discrete, so I'm going to take up a full payload slot with a VPX GPU card sitting side by side. As Ken kind of mentioned, the interconnect is going to be an expansion plane based PCIe interconnect. And depending on if you're a .11 or .13 profile, you can either hit X8 or X16. So a lot of transitioning from classical backplane topologies over to more modern SOSA-driven topologies today. This is still an applicable, acceptable environment of just having a slot-to-slot GPU, CPU side-by-side PCIe interconnect. And it's frankly a great starting point to get there. And I'll explain in detail why it's actually necessary to look at this now, even if considering Ethernet as the main data plumb for your data. And additionally, you can do more novel topologies depending on how you've routed your expansion plane. So while data plane, we've traditionally seen a lot of switch-centric ecosystems out there, expansion plane's a lot more flexible. So both at the SBC and the next slide I'll show you at a GPU complex, there are options for bifurcation. So for example, a lot of the Xeon D SBC processors out there today allow you to bifurcate at the software level your PCIe interconnect. And what that can allow is multiple endpoint devices to be connected to a single CPU complex. Here I'm putting two GPUs, but you can imagine if you're still using an FPGA over PCIe, that could be available, or a storage device. If that is not available within your SBC architecture, again, it's processor dependent. There are also options with GPUs where a PCIe switch can be deployed locally, and that bifurcation can take place within that card. So basically tacking on a additional endpoint to the GPU endpoint and then muxing those together to the final root complex. So that's a high level overview, but then to take it, okay, let's look at the backplane and actual data interconnect. Here's a traditional backplane SOSA driven environment where you have a CPU, a switch, and an FPGA, and they're going to be interconnected with one another over the data plane as highlighted here. And so that's that 100 gig Ethernet link that Nigel is referring to, that Ken's been talking about, where 40 may be acceptable. There are other planes lower tier for 10 gig and so on. But that's a pretty traditional environment of getting data over to the CPU memory complex. Once you add a GPU in here, again, it can instantly slide side by side with the CPU if that expansion plane is available. In a traditional environment, this is how that data complex is going to get passed through. So if an FPGA, again, is blasting data through a switch to the CPU, to transition that data over to the GPU, you would hit the PCIe bus over the expansion plane. And there are a lot of optimizations to make that more effective, to avoid hitting CPU memory and essentially getting more return on investment and not being bound by that CPU in the way. The one important thing to consider is with a switch-centric architecture, which a lot of the backplanes out there that are off the shelf are available, typically there's going to be a data plane per payload slot. So just because I've put in that GPU card and I'm not currently hooking up to that data plane, doesn't mean it doesn't exist. And so what I would like to propose kind of to the marketplace out there is consider a scaling architecture, and I'll explain why, prior to jumping immediately into an Ethernet GPU complex, because the slot profile is not going to change and the GPU interlink is still going to be a PCIe bound interface. So to really nail in on that, this is a discrete GPU over an expansion plane on the left. There is then a data plane interconnect on the right as we add Ethernet NIC devices locally to the GPU payloads, which are now coming readily available. But what is not available is the following. So this is not a possible environment. You can't just have your GPU and your NIC connected over Ethernet with no expansion plane interconnected to the CPU, right? It's just not possible. There are options in the marketplace where that is accessible, which isn't going to be a focus of this webinar, but if you look at different Jetson Orin platforms, which are also serviced by us, that has a local ARM CPU with a GPU complex where a single slot topology can be taken in, and there's a GPU accelerator there. But in your discrete GPU environments, again, you're bound to that CPU environment. So when we add a ConnectX-7 or different NIC architectures locally to the GPU, this interconnect becomes now available. So previously it was no connect and dormant, but now it is actually available for use. And the key thing is nothing has changed on that expansion plane interconnect. So that's still present and required. But the key here is just because that data plane interconnect is available does not necessarily mean that it's going to be efficient, right? So it's really going to take the software ecosystem to be successful here. And let me go into a little bit of detail on that. So pulling back from a backplane architecture and looking at for a more CPU focused environment or software centric environment, here's a typical flow of a CPU card ingesting data. So a lot of this isn't 100% accurate. I'm kind of representing the diagrams for sake of conversation here. But what you'll see is UDP packets coming in over a data plane into a Ethernet NIC device. There's typically some local type of buffering memory or caching on that NIC device. But then there is going to be often a local to that CPU card PCIe interconnect. So going over to the CPU complex that's running the operating system with the kernel, the application, and DDR, that data is going to be passing over PCIe into DDR memory. So that's a typical interconnect for just the CPU taking in data, as shown here. When you add in a GPU to that existing environment, again, a GPU without a local Ethernet NIC, this is how that complex looks now, right? So a PCIe device is now being added. A separate GPU driver is being initialized within the CPU kernel space. And that PCIe connection is up over the backplane expansion plane. So UDP packets coming in over the Ethernet data plane at up to 100 gigabit, hitting the NIC, going through a PCIe bus local to the SBC. Again, there are other topologies where maybe that is not PCIe, but at the same time, it is a local interconnect there. And then blasting the data through kernel over to the GPU driver and over to the GPU. When we add the NIC, what really occurs here is this topology. So in the top left there is a GPU with a local Ethernet NIC device. But the key thing to be aware of is that NIC driver for that Ethernet device is still running on that mating CPU. So we've essentially added now an additional PCIe connection endpoint that's merged via the switch. But the CPU is still the puppeteer controlling all of this. So we've unlocked access to that data plane that was previously no connect. But again, it's still being facilitated by the mating CPU in a different slot. So what's critical with adding that Ethernet device locally is you need to look at every different part of the ecosystem where memory and packets are going to hit. So I've highlighted a few here. And really what we should focus on are the ones I've highlighted. So that DP02 is the data plane coming into this GPU Ethernet NIC card. DP01 is the CPU's same data plane, again, typically connected with a switch-centric Ethernet device. We have a back plane connecting the two architectures together with PCIe expansion plane, and then again, the CPU as a local DDR complex. And what really needs to be considered by integrators and the software ecosystem as a whole is looking at why are we adding the Ethernet NIC locally to our GPU, and where are my performance gains? So if I'm trying to focus on the CPU and removing that DDR operation, opposed to am I adding the NIC because I need a direct bus available, I can't pull all the data over DP01, you can get that same performance gains via software without having the NIC locally. So again, to re-highlight that, the red object there can still be removed from the operation via Rocky RDMA, different Ethernet pull drivers, and so on. And as long as from an integration standpoint, you can accept, I'm going to be hitting the PCIe bus locally there, and I lose the performance gain of DP02. But it's really going to fall on the end integrator and the software architectures to apply a thoughtful approach to this, right? So from the get-go, when looking at classes of GPU products, you really need to consider, okay, what amount of performance is going to be available when I look at my thermals and what is available in my slot profiles. Adding in additional ICs like PCIe switches, Ethernet devices, and so on are going to potentially pull away thermals from what could be running on the GPU. So there's a counterbalance between these two. And then the bus memory needs as well. You also have to look at, long-term versus immediate needs. So because it's the same slot profile, you can drop in an existing GPU today where that PCIe interconnect fabric is required, remove, add in the Ethernet-enabled NIC once the software ecosystem is functional and deployable for your environment, and there's no changes to the actual backplane and further on. So it really needs to be looked at leveraging the software guys, the ecosystem, how is the data that is being generated from the FPGA side, as well as potentially cameras, gimbals, and so on, how is that being packetized? How do I handle, this is an IP-based system and there's probably additional headers of different types on my payload. How do I handle removing those headers and repacketizing the payload to something that I can run on my GPU engine? These are all things that need to be considered from a high-level software ecosystem that from, again, a marketplace, I think we all need to start collaborating and discussing more readily to ensure that as we deploy GPUs more and more to achieve that AI ML environment, that we're successful and the software is there as well. So that's really the gist of my presentation here. So I'll throw it back to John.
Okay, well, thank you, Chris. Now it's time to take some questions from our online audience. If you would like to participate, type your questions into the Ask a Question box and hit the send button. Also, please take a moment to complete the feedback form that will appear on your screen at the end of the webinar. So the first question is, what is MTU? Who would like to take that?
Yeah, I can take that. It stands for Maximum Transmission Unit. Apologies for the three-letter acronym. Basically, that's the amount of data that you can send in a single transaction. So I just wanted to make sure we defined what we were doing there in case anybody wanted to sort of repeat that benchmark.
And if I could chime in on that real quick too, one of the things to consider with MTUs are jumbo frames. And so when I was referring to just a couple minutes ago there, the packet sizes and the headers, your MTU is going to enforce the number of headers that are going to be applied there. So something the software environment needs to look at to achieve that full throughput or, jumbo frames and how their payload's actually being packetized.
Okay, Ken, did you have anything to add to what is MTU?
No, I think they covered it.
Okay. In the case where a single board computer plug-in card is connected to two GPUs by the expansion plane, is a PCI Express switch chip required to be present on the single board computer? Who would like to take that? Maybe Ken?
So, and Nigel or Chris might want to follow with this, but
Sure.
you could have one, or you can have the bifurcation taking place in the PCIe interface. So you peel off 4 lanes to the right, 4 lanes to the left, for instance, and then that would give you connectivity into the PCIe root complex. So, Nigel, you want to comment on that further?
Yeah, so at the SBC level, we typically offer a number of different configurations. So there's either a switch built into the processor itself that enables that bifurcation, or we fit a secondary PCI switch on some of our processor boards. And typically with SOSA primary or secondary profiles, you can have up to a by 8 or a by 16 link. If you have a by 16 link, that could be bifurcated to 2 by 8s. It could actually be bifurcated to 4 by 4s, but the SOSA profiles typically don't. You wouldn't expect that to have that type of configuration on the backplane. But there's a lot of flexibility there, and yes, the switch is there to do that.
I just like to make one point around that. In our backplane architecture, one can't always predict how you'll want to connect the expansion plane up in an architecture. So if you want to have that flexible, we've got a backplane where we don't commit the entire expansion plane mapping, and through cabling, through something called Meritech cabling, one can add those links in to obtain the, they say, the topology. For instance, if you wanted, in Nigel's example, you could have up to 4 GPUs being driven off of one single board computer. So that allows you to use a backplane in a more flexible way, or we have backplanes where we've sort of taken a good shot at what we think those connections are going to want to be to allow folks to implement 1 or 2 GPUs in a specific backplane.
Yeah, and I've thrown a slide up here just for reference, what I was talking about again. So that bifurcation can happen at the CPU if supported, or again, also could be out of the GPU. There are options also where you have, instead of an Ethernet-centric switch environment, a PCIe switch environment. Really got to consider, where is that PCIe switch going to be deployed and your power impact from that. And as Ken mentioned, cabling is a great way to test different topologies, novel and in a test environment, and then deploy to production pretty easily.
Okay. A question from the audience: have any of the GPUs been radiation tested or qualified to your knowledge? What do you think, Chris?
Yeah, so it's a very topical topic, especially when you look at, where is space going and enablement of space VPX and other things. It's one of those, definitely I'd love to talk offline further on that, and different options when it comes to levels of rad hardening and so on. So definitely reach out. Okay.
Nigel, your thoughts?
I don't have any expertise on the specifically on the GPU, so I can't really comment on that.
All right, Ken, anything to add?
No, I think Chris is the one with the access or the information around that topic.
All right. Okay. Is TSN supported today across 40 and 100 gigabit connections to minimize Ethernet latency and jitter? Ken, what do you think? Oh, okay. Go ahead, Nigel.
Go ahead, Nigel.
Well, I'll take first stab at it, and then obviously please chip in, Ken. So in reality, no, or at least in my experience. So if you want to get a product from us today, we can give you 2.5 gig, and we can give you 10 gig capable TSN capability. I should say the latency on those types of interfaces is extremely low. We talk about nanosecond latency. Now, is it coming on 40 and 100 gig? Yes, it is, but it's not there today, or at least we can't provide you that type of bandwidth today. But I would stress that most of the real-time interfaces that we're trying to migrate towards an Ethernet backplane, they are very low bandwidth interfaces. So if you want to prototype or try something out today, I think we've got something that's very, very suitable to do that.
Okay, Chris, what do you think?
Yeah, so because of the GPU complex and being hit on the PCIe side, we're just getting now into, TSN local to our products. So I think the industry as a whole, when it hits that TSN to the GPU side, it's going to be a learning curve.
Yeah. So there are specific implementations for TSN capable. I think at the MOSA Summit, we saw that in some of the booths. But it's a layered kind of a situation where you have TSN, let's say at the CPU side, TSN considerations within the hardware fabric of the switch itself, and then software that goes along with that supports the standards that are called out for TSN implementation and the configuration that goes along with that. So there's a few layers to get there, and I think industry is moving in that direction as sort of the market looks for the functionality that one will get from TSN. But as Nigel said, we're not completely there yet, and we've got to walk up to the software support of it, and then fabric considerations in the next generation switches.
Okay. Question here, are you aware of anyone in the industry currently using TSN to distribute digital video via multicast to multiple consumers? Who'd like to take that?
I can answer from trends in the video market space.
Okay.
So it's going to be interesting, especially with Ethernet and those higher backplanes unlocking, uncompressed Ethernet video capabilities. So a lot of times you would see deployments of H.264 and MPEG transport stream for sake of bandwidth limitations. But as we look at how we're going to distribute video locally within a craft, both backplane and between potentially multiple boxes, it's going to be interesting. I know obviously RTP is being utilized often for timestamping of video, be it in, ST2110 and other options out there. It'll be interesting to see once TSN, if that hits video, again, precision's going to be frame rate locked, right? So we typically talk in magnitudes of milliseconds when you're talking video versus, RF space, you really got to potentially hit way more precise. Nigel, I don't know if you have anything to add on that one.
Yes, I don't have a specific example. Obviously, I'm a UK citizen, so I know probably about 40% of the new applications that we're seeing, or new opportunities that we're seeing, have TSN requirements. It's been quite a dramatic change in the interest rate on TSN over the last 12 months. I suspect some of those probably are video-based, but I'm not close enough to know exactly, what they're doing with those video streams. So I'm sure that there probably are some out there, but I doubt there's any deployed in the defense space because we're still at quite early stages in development of TSN right now.
Okay. Ken, anything to add?
Well, kind of walking up to it where you look at traffic shaping today and quality of service for adding determinism into the network. We've got other mechanics being used and other protocols, but not specifically, I can't comment specifically on TSN implementation yet.
Okay. Well, I think we've got time for one more question, and that is, are typical SOSA applications I/O bound needing more than 100 gigabit ENET or CPU bound, such as for AI calculations? Who would like to take that one?
I think I can comment very quickly, and it's one of those. It's going to be a push-pull. So it's going to be environment dependent. I think a lot of the RF guys are really pushing forward for that full 100 gig bandwidth. But again, kind of detailing my slides where we're talking about, CPU optimizations, RDMA, and how do you handle memory? Those are going to be gates that have to be tackled. Where I would argue right now, due to software, we are probably more bound to the CPU and processing resources, managing memory and so on, opposed to the actual pipe interconnect itself.
Okay, anyone else?
Yeah, I agree with you exactly there, Chris. I think at the moment, there's other limitations in the system, but we are getting there. And I was very surprised how quickly we saw a transition from 10 to 40 to 100 gig.
Yeah.
And that is not likely to slow down.
Okay, Ken, your thoughts?
Nothing more to add.
All right. Okay. Well, unfortunately, we've reached the end of our time. So on behalf of Military and Aerospace Electronics and Endeavor Business Media, I would like to thank today's presenters, Ken Grobe, Director of Embedded Computing Architectures at Elma Electronic, Nigel Forrester, Director of Strategy for Concurrent Technologies, and Chris Fadley, Chief Technology Officer at ISO Rugged Solutions. For those questions we didn't have time to answer, we'll be getting back to you via email. This online presentation will be available on demand from the Military and Aerospace Electronics website at www.militaryaerospace.com. The link to the archive webinar will be sent to you via email within the next 24 hours. So thanks for coming. I'm John Keller, Chief Editor of Military and Aerospace Electronics.